obtained. But yeah, very, very multi-talented. It's been an absolute joy having you in lab, and thank you guys for coming to hear his defense.
Just want to be sure real quick that Zoom's actually recording, which it is. Thank you, Russ, for that really kind introduction. I just want to be sure one last time people on Zoom can see me and hear me. Okay, great. So that's got to go away. Thank you, Honkai. All right, well, thank you everyone for coming. I'm really excited to be talking about the work I've done with Russ and Pablo related to using convex relaxation techniques in robotics and some of the numerical work that came out of really working on this topic for the past 6 years. So optimization is everywhere in robotics. And the reason for that is that optimization is the mathematical language we use to describe how we make decisions. And robotics is all about decision making. And it comes in a lot of different forms. So when you're doing collision-free motion planning, decisions look like, how am I going to adjust the joints of my robot so that I can reach into the shelf without running into anything? Or if I'm doing contact-rich manipulation, I'm really thinking about what's the sequence of actions that I'm going to use to manipulate with this red dot the T into the desired position. When I'm doing dynamic and stable control, the purpose of this robot is really to shimmy back and forth so that the pendulum is upright and balanced, and it needs to decide what sequence of moves left and right am I going to be able to swing up the pendulum. So robotics is full of these decision-making problems, and the life cycle of a robotics problem in a lab looks a little bit like this. Someone more senior gives a problem description, and then an engineer, a grad student, someone's going to spend a lot of time taking that plain language description and writing out some mathematical model. Now, if your mathematical model is in any way accurate, it's probably going to be too hard to actually solve with techniques we have. So what we're going to do is probably approximate it, and then once we have some reasonable approximation, a computer's going to burn a lot of energy and eventually try to solve the problem and output some sort of solution. Now, the class of models I'm going to be talking about today are what are known as polynomial optimization programs. So polynomial optimization programs, you model your problem in this framework where you think about minimizing some polynomial costs, and you have a list of constraints or rules that say some polynomials need to be positive and some polynomials need to be equal to 0. Now, this class of problems is extremely expressive. I'm going to show you a bunch of robotics problems that can be modeled with this language. But the thing that's tricky about them is, since they're so expressive, they're really hard to optimize or get solutions out of. So they're non-convex and NP-hard in general. So polynomial programs can encode some pretty crazy-looking functions. And so that was sort of what makes them both good and bad. On the other hand, at the other extreme of the models are what are convex or conic programs. And these are the programs I'm actually going to do computation with in this talk. And a conic optimization program is restricted to only having a linear cost, and you're required to have linear expressions lying inside some cone. So the way they look is you've got some cone, and then you've got some slice cut through in space, and you end up with a convex looking region. And these are programs that you can solve to global optimality by following the direction of the cost until you get to sort of the best point in the whole set. And so what's nice about these is that they're polynomial time solvable. You ask a computer, they almost always give you an answer. So these two classes of problems are really going to be the two models that I care about solving here. And so why polynomials in robotics? In the top three frames are three different projects that I've worked on during my time at MIT, where we use polynomials to model robotics problems in collision-free motion planning, contact manipulation, or dynamic and stable control. But other researchers have spent a lot of time formulating other canonical robotics problems using optimization. For example, in pose estimation, in some work done a few years back by Luca Carlone here at MIT with some of his students, you're thinking about how do I align two objects to understand where they are relative to each other. Or other researchers have used polynomials to encode the inverse kinematics problem. How do I position my joints to reach some spot in space? And polynomials are everywhere in polynomial dynamical systems. We use them to sort of study what areas of space a robot that's acting very dynamically can reach. And one of the reasons to use this class of problems is because it allows us to do something very principled when going from a polynomial model to something that's more approximate or maybe easier to solve. And so the first thing I'm going to argue is that polynomials, real robotics problems have polynomial structures, and we can exploit that structure. The second thing I'm going to talk about is that polynomial models have a really principled way of going from the hard description to a relaxation that is much easier to solve. And these convex relaxations can be both effective at solving the robotics problems and fast to solve if they're used correctly. And finally, I'm going to argue that structure-aware solvers can push the frontier of what we can solve in practice. Now, once I have a solution to my approximate problem, there are two natural things I can do. One is maybe the solution is good enough that I can use it to generate a solution to my original problem. If not, maybe I can use it to refine my relaxation and get an even better approximate model that I can still solve in practice. And both of these, I think, are exciting areas for future work. So in this talk, really what I'm going to focus on is arguing that synergizing across the entire pipeline of modeling, relaxing, and solving can lead to both better models, better relaxations, and finally better solvers for the problems that you have in mind. So with that introduction in mind, I'm going to start my talk by focusing on the modeling side, some work I did of using polynomials to address kind of an interesting problem in robotics, and that's going to be collision-free motion planning. So collision-free motion planning is sort of everywhere in robotics. We want our robots not to crash into things. But one of the things that makes it hard is that if you want a very precise robot, it's going to get close to stuff. And what I'm showing you here are two trajectories that differ by 20 millimeters. The thing is, when I actually play these trajectories back, on the left, you're seeing what used to be the blue trajectory, and it's going to be perfectly fine. On the right, that 20 millimeter difference corresponds to me clipping the shelf, which is going to toss it around and result in a much worse behavior. So why is collision-free motion planning so hard? And the reason for it is that there's really two fundamental spaces at play. One is what a fancy word roboticists use for the real world is task space. And this is where we define our task and say, I want my robot to reach in space. So my task space robot here has only two joints. It can only move either the left pinball machine or the right pinball machine. Mathematically, roboticists, they think about doing motion planning by mapping each of these joints to a different coordinate axis. And this is what's known as configuration space. So here I only have 2 degrees of freedom, and so I can actually visualize it. But in general, my robots have a lot of degrees of freedom, and therefore this is going to be some arbitrary n-dimensional space. In motion planning for roboticists, the reason we like this space is that there's this, the robot becomes a dot. In motion planning, it corresponds to just finding some curve in this space that's not going to intersect the red region. And so in this line of work, what we do is we give a principled method for certifying that an entire full dimensional region in configuration space contains no collisions. And this is sort of the first efficient method for doing these full dimensional regions in configuration space. We're also going to give a method for actually growing these regions in practice, because in high dimensions, just guessing a polytope is just not going to be feasible. In this chapter, if you're interested in this line of work, we also show that you can certify just a trajectory much more efficiently than the full dimensional case, and also how to go from doing one region to many regions, but I'm not going to have time to talk about that today. So how do I convince you that a robot is not going to run into anything? If I have a robot and I think about its end effector A here, I can convince you it's not hitting the cone by drawing a line between the body A and the body B. And for this line to sort of be a valid certificate, what this is a hyperplane, and all of the points X in the body A need to be on the positive side of the hyperplane, and all of the points X in the body B need to be on the negative side of that plane. The tricky thing is, if you give me just one plane, that's going to work at one configuration. But as the robot moves, that hyperplane is going to need to move in order to actually continue certifying. So I don't just need one plane. I need a function or a family of planes that's going to work over the whole configuration space. So this for all X condition is already infinite dimensional. But in a lot of cases for robotics problems, we can actually write this down as just a finite list of constraints. And so, for example, for the body A, it's enough to just check that all the corners are on one side. But now the thing is, I have to find a function that's positive over some set. And it's going to be hard to do this globally. And so what I'm going to do is I'm just going to restrict myself. And now we see configuration space enter again. As I move my robot over some part of configuration space, I need these functional inequalities to actually hold over the whole space. And so now I'm going to talk about a method that we use, known as the sums of squares method, for verifying these types of functional inequalities. And so I'm going to go back to sort of the high level. if you give me a polynomial P and you want to know, is this polynomial going to be positive over some set defined by polynomial inequalities and inequalities, this is going to be hard to check in general. On the other hand, I can convince you that this polynomial is actually positive by writing it in kind of this funny way. The sigmas are going to be what are known as sums of squares polynomials. And so since there are a bunch of squares, if you put in any x into them, they're going to be positive. They're going to give back positive numbers. And so the reason this should convince you that P is positive on the set is that the first term is positive everywhere. The second term is positive everywhere times something that's positive on the set that I care about. And the last term is 0 on the set I care about. So if you give me an x in this set, this is going to be positive on that set. So this is going to be a sufficient condition, and this certifies that P is positive. So the nice thing about this type of formulation is that the first equation is a linear constraint between the coefficients of P and the coefficients of the sigmas and the lambdas over here. The second equation, it can be written down as a positive semi-definite constraint. And when you hear that, you should just think convex. And so this is going to be something that I can use something like semi-definite programming, which is a convex program, to search for efficiently. So when you expand this out, you have your task space certificate, which is going to be some hyperplane in the real world. And simultaneously, you're going to be looking for a configuration space certificate, a proof that the proof is a proof. So this convoluted way of writing out the problem, if you jump through all these hoops, you end up seeing that semi-definite programming can actually find certificates of non-collisions for all the configurations in this space. And so we can actually search for these very efficiently. And that's what we're doing here. I've certified that every single polytope in this configuration space doesn't contain any collisions. And what you're seeing is between the two tips of the robot is the hyperplane and task space that I'm proving is separating those two things. And so there's a proof that the robots will never cross that hyperplane. And as I switch regions, the hyperplane is going to change. So now that we have a way of certifying a region, guessing a region is going to be intractable. So how do we grow these regions organically? And the method for doing so has a lot more symbols than even that one. And so it's a lot easier to explain in a picture. If you give me a polytope in configuration space, I can think about approximating its volume by just inscribing an ellipse on the inside. And to grow the region, what I'm going to think about doing is I'm going to try to push the faces of the hyperplane away from this ellipse as much as I possibly can. So my objective is maximize the new offset, subject to this new polytope needs to continue to contain the old ellipsoid. That's something I can write down in a convex way. And then I also need to not violate the proof that this guy is not in collision. And so if you crank through all of this, you're going to see that you end up with another semi-definite program. And you can actually alternate between these two semi-definite programs to grow the regions. So here what I'm showing you is an animation where we started with a really tiny polytope centered at all of the dots. And over time, you can see that the polytopes are growing to fill out the entire space. So this is one way that you could use to generate a provable cover or a provable description that where the robot can be without colliding. And so the first question you might ask is a convex region in configuration space even a meaningful thing to look for? And the answer is yes. A single convex region is actually big enough. What I'm showing you here is the robot dancing around just one of the regions. And it's able to approach the object, move around, maybe try a few graphs and pull out, all within a single convex region. Additionally, a lot of people get scared of semi-definite programs because of the scaling, but this method remains practical even for high degree of freedom robots like 12-degree manipulators by manual systems. And finally, when you restrict the method to just certifying collision, certifying just a trajectory, the method is extremely fast. You can actually check collisions really practically in less than a second for really complicated motion plans. And the method is also precise enough to discriminate the safety of the two trajectories I showed you at the beginning, which only differ by 20 millimeters. So that's a little bit, I'm hoping, convinces you that going from a problem description to a polynomial model can be quite powerful. And this is something that has been done in a ton of other work. And so now what I really want to focus on is going from, okay, I now have a polynomial model. It's useful. What kind of computations can I do with it? So I showed you one way of doing relaxations. Now I'm going to move on to how do I actually do optimization. So in order to do optimization, I need to introduce a little trick that Pablo introduced in his thesis way back when, which was how do I go from a polynomial program to a principled convex relaxation? The first trick is I'm going to think about taking the polynomial and I'm going to rewrite it in a particular way. I'm going to imagine to do optimization, I'm going to take my polynomial and I'm going to try to drag it down to the x-axis until it just becomes negative. What's the most I can drag it down so that over the set that I care about, it's going to become negative. Now, this looks like I haven't done much, but remember that I showed you a method for checking whether a polynomial is positive on a set I care about. So what this does is by replacing this condition right here with the sums of squares type relaxation, which again is a way of proving that this polynomial is positive, I'm going to generate a family of semi-definite programs that approximate this problem better and better. And they're going to be indexed by the degrees of the polynomials sigma and lambda. And so that's going to give me a hierarchy of polynomials, of relaxations. And the key takeaway is that this is a semi-definite program that's polynomial time solvable. So what's good about this? It produces a hierarchy of semi-definite programs indexed by maximum degree. And as you turn up the degree D, the solutions get better and better. You approximate your original program better and better and better. The downside of this is that it doesn't scale very well in degree. So if you have a program with n variables, the program scales as OD to the n. And so if you want to turn this degree up very high, you're going to pay a very heavy cost for it. And so really using this technique in practice is all about trading off between the power of the program and the efficiency of actually solving the relaxation. So that's going to bring me to my work on how do we actually practically tighten sums of squares relaxation. Degree is a very blunt hammer. And so I'm going to talk about some work that we did on how to find better ways of maybe strengthening your relaxations. And so in this part of the talk, I'm going to focus on quadratically constrained quadratic programs, which is a subclass of polynomial programs that's incredibly popular these days in robotics. So QCQPs are just programs that have quadratic costs, some quadratic equality and inequality constraints, and some linear constraints here. And these are the class of programs that Bernard used to sort of describe the mechanics for the planar pushing task I keep showing. And it's also the class of problems that several researchers have been using to do robust rotation estimation. So in this problem, what I'm trying to do is I have the blue point cloud of the bunny, and I'm trying to figure out how does it match up or align with the pink point cloud. And so these are going to be the kind of the two examples that I run with for this particular problem. So why do roboticists like this, this framework? It's got a really easy way from going from the hard problem to a semi-definite relaxation that's a lot easier to solve. So how do I go from the program on the left to the program on the right? So the program on the left is not convex because I have not assumed that Q and P are positive semi-definite. So what I need to do is I'm going to start by lifting from the X variables to some matrix X by taking an outer product. The next thing I'm going to do is I'm going to apply the trace trick. So the trace of X transpose QX is going to be equal to the trace of QXX transpose, which is going to mean that I can express my quadratics as linear functions in the variable capital X. And so here, all of the quadratics have just become linear functions. And the only thing that's left to do is the constraint that X is equal to XX transpose is very hard to actually optimize over. And so we're going to relax it away into a semi-definite constraint. So these programs are essentially identical. The only difference is I've replaced the X is equal to XX transpose with this relaxation. If I were to solve this problem and get a rank 1 solution, that'd give me the globally optimal solution. And if not, it's going to give me something that's weaker or an approximation. So how does this relate to what I was talking about? This is actually completely equivalent to the first level of the sums of squares relaxation. And importantly for robotics, this is actually the only level of the hierarchy that solves fast enough for most robotics applications. And so it's really sort of the canonical polynomial optimization problem. Unfortunately, it's frequently too weak without doing a little bit of extra work. And so now I'm going to describe what that extra work looks like. And so what is that extra work going to look like? We could go up in degree. The problem is that is a very blunt hammer. And like I said, this is not going to scale and we're not going to be happy with the solve times. The observation that's been made over and over in the literature in various contexts is that sums of squares relaxations are extremely sensitive to how you wrote down the original polynomial problem. So here I've got two polynomial optimization problems. They have the same cost. They have the same first constraint. And the second constraint is essentially the same thing. Both of them are encoding that x has to be 0. And the only difference is this one is x to the fourth and this one's x squared. If I take the sums of squares relaxation of the guy on the left, it's going to give me something completely uninformative, a lower bound of minus infinity, which is not helpful. If I take the one on the right, which is essentially the same problem, it's going to give me the globally optimal value of 0, and I'm going to be able to recover the value of 0 from it. So if you ask a computer to solve the sums of squares relaxation of these two things, very different things happen. So we're going to exploit that. If I have a quadratically constrained quadratic program with only equalities, and I look at its Shor relaxation, every quadratic equality on the left shows up as a linear equality on the right. On the left, if I add a completely redundant linear equality on the left, it's going to show up in the sums of squares relaxation on the right. The thing is, it being redundant on the left does not mean that it's going to be redundant on the right. It might actually strengthen the relaxation in very non-trivial ways. And this has been reported over and over in the robotics literature. For example, in the teaser paper, they spend a fair bit of time explaining how important it is that they add certain tightening constraints. And so I wanted to see what is actually the effect of them reformulating their problem with these extra redundant constraints. Remember, ideally, this gives a rank 1 solution. And so a shift left is a good thing. Here I'm reporting the numerical rank of the solution X in the robust rotation estimation problem. Without any redundant constraints, the best you get is rank 4 every time. If you add these redundant constraints, you recover the globally optimal solution more than 60% of the time, and you can round it to the optimal solution even more frequently than that. And here I'm showing you how much of the gap is. And again, all you need to notice is that adding this constraint shifts the graphs left, and that's a very good thing. So what do we show in this part of the thesis? We describe a method for finding all the quadratic implied inequalities that can be found cheaply. So there might be ones that you can add that are hard to find, but we don't want to look for them because it'd take too long to find them. We also find only the equalities that provably tighten this guy on the left. Not everything that I add here that's redundant will help the thing on the right. Additionally, the method is going to be fast enough to be used as a pre-processing step for robotics. And finally, in the thesis, if you're interested, this actually generalizes to arbitrary programs. It's just a lot easier to describe for QCQPs. So what do? If I have a polynomial optimization problem and I want to add a new hat x equals 0 constraint to it, one way that I can parameterize sort of the set of everything I could possibly add is if you suggest to me a hat h, I can say this is definitely redundant if I write it in this way. And similar to the sums of squares stuff before, hat h is 0 where I care about because all of the hi's are 0 where I care about already. So this is a way of parameterizing everything I could add. And so we call hat h, it's known as a valid equality. And for those who are like algebraically inclined, the thing on the right is the ideal membership certificate for hat h. And the important thing, if you're not algebraically inclined, is that this is a linear condition. It's a linear function between hat h and the mu i's. Okay, so that's just how you find all of the equalities right there. It's very simple. For the next thing that's maybe more important is when can a new constraint actually help tighten the relaxation, right? So when is this polynomial optimization problem, the relaxation of this guy, going to be tighter than the one on the left? And we give a simple degree bound or a simple way of testing whether a hat h is actually going to be, can even help strengthen. It's a necessary condition. And the degree bound is related to if I have a polynomial hat h of degree d hat, there's some condition you can write on the left. But the important thing is that this is, again, going to be a linear condition between the hat h and the mu i's. So what does this look like for QCQPs? You can write out a very concrete linear system on the left. And the usefulness condition is just that you need that the new p hat needs to not be in the span of the original thing. And so both conditions, once again, they're linear in the hat p's that I'm looking for and the mu i's that I'm looking for. And so after fixing a degree for these multipliers, this is what I mean by the ones that can be found cheaply. After you fix a degree, this boils down to just a big linear algebra computation that is actually very fast. And again, for those that are algebraically inclined, what this does is it's a Macaulay matrix method for computing the low degree quadratic part of the ideal. So the first thing you might ask is, can you even find the implied equality constraints cheaply? And the answer is yes. So when you formulate the planar pushing QCQP relaxation, the sort of canonical quadratic equalities are I have to make decisions about certain rotation matrices and variables u and w. And since everything is a decision variable, this is quadratic. And even encoding that something is a rotation is a quadratic constraint. And so these are sort of the prototypical constraints, and the method recovers sort of what I would say are the obvious additional constraints. But the thing that's not obvious is that these actually can provably help the relaxation. So the method recovers the ones that you would expect. And it does the same thing for the robust estimation problem. So in the teaser paper, you could have asked a computer to actually generate those semi-definite relaxations for you. That would have been provably better. Additionally, keeping only the implied equalities is extremely important. If you try to add everything, there's over 22,000 things that you could add in the planar pushing QCQP, and that's just going to grind your solver, like slow it down a ton. But if you only add the things that actually help, it's actually very few constraints. And so it's very important that you only do computation with those. And finally, since we're only computing the smaller number, this is actually super fast to do relative to solving the SDP. The SDP takes on the order of half a second to 2 seconds for the planar pushing case. And the robust estimation problem is like instant. It's less than 100 milliseconds. And in both cases, you take less than between 1.5% and 1% of the SDP time to strengthen your relaxation. So this is worth doing ahead of time for certain problems. So that sort of concludes the part of my thesis that goes from polynomial model to a stronger conic relaxation. Now I'm going to move on to solving. So we have polynomial models. We design the convex relaxation of these sort of in the same way over and over again. And so is there something there that we can actually exploit to make better solvers that are aware of the structure? So the class of problems that I'm going to be interested in are sort of these mixed discrete continuous optimization problems. So robotics is kind of full of these. You have, we encode these as mixed integer convex, some sort of continuous program. And the reason that these are really natural in robotics is that in robotics, a lot of times we have to make discrete choices. So for example, if I'm the robot pushing the T around, where am I making contact? When am I making contact with the actual T object? Which bin am I actually going to reach into or not? But then there's also a continuous component. If I've decided I'm moving between bin 1 and 2, what's sort of the continuous trajectory I take? How hard am I pushing the T? And so on. So this is a class of problems that we really care about solving. And one of Pablo and Russ's former students came up with a really nice way of encoding these problems, which is known as the graph of convex sets. So the graph of convex sets, what it does is it thinks about modeling the discrete part of the problem as a classic graph problem. So in a classic graph problem, I have to, I have a problem, I've modeled it as a graph, and I want to do something like find the shortest path in the graph between V1 and Vn. So the discrete choice here is, do I include some edge in the graph or not? Do I include some vertex in the graph or not? And when I'm solving these types of optimization problems, I'm going to pay a fixed cost CV and CE at every vertex and every edge. And it's not going to change. It's just a discrete choice on or off. What Tobia did in his thesis is he extended the idea of a graph to include a convex set at every vertex and every edge. So what he does is he attaches a convex program at every vertex with a convex, so that's a convex set plus a convex function. At every edge, you attach a convex set that's going to be on the variables of the two endpoints of my edge. And so this is also going to have a convex function. And so when you move to choosing a subgraph here, what you end up doing is not only do you have to pick the discrete, include the edge or vertex, you also have to pick a point in each of the sets. And so you're going to pay a cost that the cost of choosing an edge or a vertex is going to change depending on the set of points that I pick in each vertex and each edge. And the key thing here is that, like many problems, the extension inherits a ton of structure from the original problem. So when you have a classic graph problem, a lot of times you encode it as a mixed integer linear program, and the GCS extension looks very similar. The graph problem is completely the same. It stays there. And the cost, all we've done is sort of extend it to be continuous functions of new variables. And the thing that I've done to extend is that the thing that Tobia does to extend is basically you add a convex program at every vertex and a convex program at every edge. So there are a lot of symbols here, but the key takeaway is that the graph of convex sets extension is a generalized polynomial optimization problem. The generalized portion of it comes from the fact that these cones don't need to be polynomials, but sort of the techniques you use to relax it look very, very similar to the sums of squares relaxation. And designing an efficient relaxation is non-trivial. That's a big part of Tobia's contribution there. But the key point is that the relaxations get big really fast, especially as the graph grows. And additionally, the relaxation inherits a ton of problem from the original structure. The graph structure of the original problem gets inherited as a graph structure in the convex relaxation. And finally, the actual convex relaxation technique puts a little bit of more substructure on the inside. And I'm going to talk about that briefly at the end. So that's going to bring me to the third and final part of my talk, which is going to be about solving convex relaxations of these problems. And I'm going to talk about some first order solvers, some structured linear algebra, and then how we apply it to graph convex sets. So the first thing you need if you're going to talk about solvers is a benchmark. And graph convex sets has been used in several papers, but the interface or the way that we collected them is kind of scattered. So the first thing we contribute in this part of the thesis is actually a benchmark and some unified framework that you can actually interface with and try your solvers on. And so when you solve these problems, you'll see that some of the solve times are actually pretty good. So the mazes in the mazes in this problem, they solve, I've got some small mazes that solve in less than 100 milliseconds. I've got some surprisingly big mazes that solve in less than 4 seconds. So we're kind of happy actually with these types of solve times. And the graphs for the EWA shelf and the bimanual setup, they're not very big. And so you can actually solve them somewhat efficiently. The solve times start becoming a bit more of a problem when you start having bigger graphs with more complicated sets. And that's, for example, in the planar pushing case, the solve times can push up to a couple of minutes. And Xiao did some work where he created some enormous graphs that were not contrived because they're encoding problems we actually care about, which is manipulating multiple objects at the same time. But centralized solution methods to this for the relaxation just don't work. If you wait, you can wait a day and maybe it'll take a step. So what do we do in this chapter? This chapter is sort of in 3 nested parts. The first thing is we're going to introduce the Vega solver, which is designed for it's a first order solver for massive graph of convex sets instances, sort of those bottom 2 examples that I was talking about. Vega is going to be built on top of C-Cosmo, which is a highly customizable first order conic optimization solver. And the customization part of C-Cosmo is going to be built on top of some matrix equation work that we did for how you solve the particular linear system that shows up in that solver when applying it specifically to some of the subproblems in Vega. So again, what is the structure that I'm targeting? GCS has a conic program at every vertex, a conic program at every edge, and some global graph problem. And the reason centralized solvers sort of fail on really big instances of this is that it has to consider everything all at once. And so in order to solve this, what I really want is some solution technique that lets me exploit the fact that my problem comes in these chunks. And the sort of classic algorithm for doing this in convex optimization is what's known as ADMM. So ADMM is an algorithm for solving convex optimization programs that are presented in a very particular form, which is minimize some convex function over some alphas, minimize some convex function G over some betas. And the only types of constraints that are allowed are that the alphas have to equal some of the alphas have to equal some of the betas. And the algorithm is extremely simple. You can parallelize over all the different alpha i's, and it just corresponds to take your convex function, minimize it with some additional quadratic regularization, take your G functions, minimize it with some additional quadratic regularization, and then basically push this U value up so that alpha and beta get driven to be equal at the end of the algorithm. So why do we like this algorithm? It decomposes big problems into simpler subproblems. So if I try to solve this all at once without doing any sort of decomposition, I'm going to be left doing really big operations. This is very useful. Additionally, what's nice is that the steps 1 and the steps 2, they parallelize across the subproblems. So the alphas and the betas are all different. And so you can parallelize across this very well. And finally, the algorithm is super simple and it converges to a low accuracy solution relatively quickly, which is all we need for the graph of convex test relaxations, because you don't want to solve a approximate problem very accurately. You want to solve the original problem accurately. So that's going to bring me to like how we design an ADMM split for Vega. And that's going to be basically, I need to find some way of massaging my GCS relaxation on the right into the form on the left. And in order to do that, it's important to look at, okay, how are my variables even interacting? Why can't I apply ADMM out of the box? And so what I'm going to do is I'm going to describe a way of teasing apart these variables that will allow us to use ADMM directly. So if I look at a sequence of 3 vertices, U, V, and W, that are all connected, and I look at how the variables are sort of interacting through the constraints. The blue variables are sort of isolated to each vertex. I don't really need to do anything about them. The orange variables, they're global. Every program has essentially every variable. The red variables, on the other hand, they show up only at an edge and at the adjacent vertices. So the first thing I'm going to do to tease apart this problem is I'm going to introduce a bunch of copies of the Y variables. At every vertex, I'm going to introduce a local copy of what that vertex thinks the flow variable through that should be. What this does is it takes the graph problem away from all of the convex problems. And so now I just have a pure graph problem right here, and then some additional equality constraints. For the edges, they've already completely decoupled at this point. The only thing that's left to do is to decouple some additional edge variables that are showing up in the vertex convex programs. And so to do that, I'm just going to do the same thing. I'm going to duplicate more variables. So this is a very classic way of taking a very complicated problem and sort of teasing it apart for ADMM. And the key thing is this particular splitting method, what it does is it decouples into a graph problem, a convex program at every vertex, and a convex program at every edge. So what do my ADMM steps look like now? What I need to do is at every vertex, to solve sort of the first step of ADMM, I'm going to need to solve a conic program with quadratic cost. Graph, same thing, a quadratic program at every cost, at a quadratic program over the whole graph, and a quadratic conic program at every edge. So this block right here, I can parallelize across the edges, and this block right here, I can parallelize across all of the vertices and edges. And then the graph problem is typically much smaller relative to the convex part of the problem. So that is the Vega solver in a nutshell. We design a particular ADMM split that teases apart the GCS problem into sort of its canonical parts. Yes.
I hope I can answer the question.
Please
Can
do.
you go back to the previous slide?
Yeah.
So when you say the graph problem tends to be much smaller, what are you talking about?
I'm saying that the graph problem has one variable at every vertex and one variable at every edge, but the conic programs can have tens to hundreds to thousands of variables at every vertex or every edge.
And how big is the graph?
So the graph for this is on the order of 900 vertices and 1,800 edges. The one for this is on the order of 8,000 vertices and 15,000 edges. So the benchmark has really diverse shapes. So for example, this is 11 vertices and 20 edges. So tiny graphs. So we've got big graphs, tiny programs. We've got small, tiny graphs, moderate programs, and we've got sort of everything in here. Okay, so that concludes the Vega portion of this part of the thesis. And so now what I need to convince you of is that you can solve a quadratic conic optimization program as the subproblem effectively. That in and of itself should raise flags if you're in convex optimization. So what are the requirements for Vega for solving this quadratic cone program? Well, I need to solve it to moderate accuracy. I don't need to solve it to 10 to the minus 8 or 10 to the minus 16 precision. Most importantly, maybe, is I need to be able to amortize the fact that I need to solve these programs repeatedly by warm starting. So I need a method that lets me warm start. And finally, I need whatever method I use to be able to exploit any additional structure that I might have at the edges and the vertices. So that's going to move on to the C-Cosmo solver that I wrote, which is a highly customizable first order conic solver. And it targets these types of programs by, again, applying ADMM. And the reason for that is ADMM is super, super easy to warm start. To apply ADMM to this problem, what you do is you introduce a slack between the linear subspace and the cone. And so you ask that your X and your S need to live in the linear part of the program. And then you introduce copies of those variables that you're going to ask to live in the conic part of the program. And what C-Cosmo does is it alternates between minimizing with respect to the linear part and minimizing with respect to the cone. So the steps themselves are very efficient. The first step is you solve a linear system that's related to your problem data. The second step is that you do projection onto the cone. And the third step is going to be your classic dual update. It's vector addition. It costs almost nothing. The expensive part of this is going to be solving the linear system. And that's really what we're going to focus the last part of the talk, or the last part of this nested part on. And importantly, so this is the most expensive part. Unless you're solving a semi-definite program, then that can get expensive. But this is the whole algorithm. Now, this algorithm is not mine. Bart here wrote the OSQP solver based off of this algorithm for quadratic programs. And then his advisors group continued work and wrote Cosmo in Julia. And so at first glance, C-Cosmo is a C++ port of Cosmo, but we do some additional enhancements on top of it. So for, again, those who are expert in ADMM, we implemented every acceleration technique that I could do in a reasonable amount of time. And you can see the whole grid of which ones actually help and don't. The other thing is that C-Cosmo is not just one implementation. It's actually a family of implementations, and it's designed to be this modular thing that you can build on top of. So the standard form of a conic quadratic cone program looks like this. And this is sort of the natural form that the edge and the graph subproblems show up in. But maybe a more interesting standard form is the matrix standard form. And this matrix standard form falls out naturally at the vertices because of the procedure you use to form the convex relaxation in GCS. And this procedure is very typical of other sums of squares programs. And so I'm really excited to try to apply these techniques on other sums of squares optimization programs. And so this is the natural form for Vega. And then since there's so much parallelism, we got interested in whether we could write an efficient batchable problem, a batchable version of the solver. And so we have a GPU version that actually accepts large batches of very small problems. And why that emphasis, I'm happy to talk about that offline. So the standard form, OSQP, SCS is another ADMM solver, both written in C. We achieve essentially the same performance just because it's the same algorithm. But relative to using Julia, we do see the differences between C++ and Julia show up. On the other hand, the matrix standard form, solving the program in this form rather than converting it to standard form actually has significant advantages. So we see between a 20 and 50% speed up on sparse instances, and on dense instances, you can see orders of magnitudes in the tens to hundreds to thousands, depending on the size that you have, and I'll get to why that's the case. And finally, for the batchable solve, batching optimization is actually very difficult to do. And so on a GPU, we see between 3 and 9 times speed up on large families, depending on, it's actually more a function of how big the programs are. Bigger programs parallelize better than this batch size. So why are we able to solve matrix standard form problems so much faster? And the reason comes down to when you are running C-Cosmo on this type of program, you end up having to solve a linear system. And the linear system that you get has a natural matrix form, and accelerating this one step, this one linear system solve, drives all of the gains across the algorithm. And so that's going to be the final part that's in this part of the thesis is solving matrix equations, which is, we covered 2 equations in this part of the thesis. The only one that's relevant to Cosmo is this type of it's not symmetric, but it's a positive semi-definite matrix equation of some kind. And the key thing is that the sort of typical classical way you would do this to solve this is that you would ignore all the matrix structure and just flatten the equations. When you flatten the equations, what happens is this actually corresponds to an enormous linear system that's of roughly size m times n. And so you end up needing m squared times n squared memory to compute with it and m cubed times n cubed time to solve in it. On the other hand, if you treat it as a matrix equation. So we show you that what you can do is you can simultaneously diagonalize the left factors and the right factors, do some transformation in those bases, and then back out the solve. You can actually do this very effectively, and this ends up working directly on the matrices. And that procedure is an hour talk. And so really the key takeaway is that this is by staying in matrix form, you're dominated by the size of the biggest matrix. You take m squared plus n squared times and m cubed plus n cubed time. And you can see this order of magnitude separation very quickly. So what I'm showing you here is in blue is the result of solving different sizes of this problem using our method. In red, you're going to see what would happen if you just did the flatten it and used sort of a typical solver. And in green, you're using something that's called the Bartel-Stewart algorithm or a variant of it. And you see that they also do things with this matrix form. And so they also get this order of magnitude separation, but they're much less efficient in the small regime. And so it takes a little bit longer for them to start beating the vectorization form. You have to get up to about 24 by 24. So that's a brief interlude into solving matrix equations. The key thing is that if you solve matrix equations more efficiently, your optimizers are going to get faster. Those matrix equations are structured arise because of the sums of squares procedure. And by doing so, you can write solvers that are much faster for that particular problem. So that is sort of how we drive some of these gains in C Cosmo and actually are able to sort of do better than you would naively expect from just re-implementing a different algorithm, the same algorithm. So finally, I want to tie it all together. And so by tying it all together, how does Vega actually perform on our GCS instances? Remember that the key computational bottleneck in Vega is I need to solve a bunch of quadratic conic programs repeatedly. And so Vega is itself an ADMM splitting for the GCS structure. And internally, C Cosmo, which it's built on top of, is using ADMM to solve the thing. So there's ADMM inside of ADMM. And you can imagine a ton of ways of rearranging this algorithm, but this is just the way that we did it. And so because C Cosmo is an ADMM solver, it naturally warm starts. And so we get that advantage for free. And since we use the matrix standard form for the vertex programs and the vector standard form for the edge and graph programs, it's sort of like adapted to whatever problem it's actually solving at the time. And the other thing is that since it's a family of solvers, we use dense linear algebra at the edges because those programs are typically dense. We use sparse linear algebra at the graph, and you can sort of the Vega reconfigures itself for those instances. And so additionally, we don't solve the problems to optimality at the beginning. You solve inaccurately first and tighten as you need to, as you go. So what does this end up looking like? On the small programs, it is not worth introducing the additional parallelism. So these graphs, to Rob's question, are very, very small. And so you don't see a lot of benefit from splitting the problem more because it introduces a ton more overhead and a ton more memory management. So what I'm showing is the centralized solve time, how long Vega actually takes to solve on my laptop. And I'm also showing you the critical path, which is sort of, if you had perfect parallelism and no overhead, how long could you actually expect Vega to take? And the critical path doesn't really start to become competitive until you get to a bigger graph. On the other hand, Vega is already competitive on the semi-definite programming examples because it is able to sort of break apart some of the harder semi-definite programming things. Additionally, Vega is able to solve the contact graph problem to optimality in 10-ish minutes, which is a huge step up from 2 hours of no progress. And the critical path there really shows you that this would substantially benefit from more parallelism. So this is parallelizing on my CPU. I have not actually connected the GPU to this. And so you could maybe hope to get closer to these numbers if you were to do that. And so what Vega represents is, since it's really designed for this extreme case, the key contribution here is that by using this technique, we're able to prove a first lower bound on this problem. Xiao's paper, he was really interested in finding upper bounds, feasible solutions to the problem. And so we now know that on this particular problem, there's about a 50% gap between these two things. So some conclusions. So this thesis really tries to go through the whole pipeline from high-level problem description to a polynomial model to relaxations, relaxations to actual solving techniques. And what I tried to argue is that polynomials can effectively model surprisingly complex robotics problems. Additionally, sums of squares gives a really powerful way to convexify these problems so that I can actually solve them and use them on a computer and actually do something with them. And with the right formulation, these sums of squares relaxations can both be solved efficiently and also be sufficiently powerful for actual practical use. Additionally, structure-aware solvers can push the frontier of what can be solved in practice. And we can solve large-scale sums of squares relaxations for robotics problems and actually use the solutions effectively. In future work, I'd really like to focus on these other two arrows. How do I take an approximate solution and use it to either refine the relaxation, which is how do we use a solution of a bad relaxation or a weaker one to formulate a stronger relaxation that's still tractable? There are hints of this in the literature in other forms. For example, this happens all the time in mixed integer programming via things like branch and bound. On the other hand, what would be a way to sort of avoid having to solve multiple relaxations? What is the relaxation version, the sums of squares version of a feasibility pump or a large neighborhood search from mixed integer programming? Can we design strong relaxations that facilitate ways of rounding to good upper bounds? So that's sort of covering what I wanted to talk about today. And now I can move on to acknowledgements. So Russ and Pablo have been the absolute best pair of co-advisors you could possibly ask for. And I think part of what makes them great as a pair of advisors is that in a lot of ways, they're two sides of the same coin. So intellectually, you can't ask for better role models. They both have this incredible ability to cut through all the noise and the technical fluff and really get at the heart of what are the real problems in the field and understand what makes a problem hard in the first place, and do we even have a way to address a hard problem? Intellectually, Pablo is one of those people that makes the world of math just seem smaller when you talk to him. He sees connections everywhere. The number of times I've read a paper and he says, this is the same thing as the one you showed me last week was kind of eye-opening. But he pairs this ability to shrink the world of math with incredible humility. His favorite phrase that all of his students, I'm sure, have heard is, I don't understand. And he says that because he genuinely thinks you know something he doesn't. But I quickly found out that frequently Pablo doesn't understand because he's 4 steps ahead and your conclusions just don't make sense. Russ, on the other hand, he really embodies the curious engineer to me. He's always looking for what is the best tool to solve robotics. And he really means that. And he really wants to figure out new ways to push forward whatever tools he currently has. He really has his finger on the pulse of what matters, how to find an interesting problem, scope it, tackle it, smooth it. It's been a real pleasure to get to know both the smooth and the sharp edges of robotics through his eyes. I think striving to live up to both of their high standards and ideals has been the most challenging and rewarding part of graduate school. Even better, Russ and Pablo pair these high standards with a passion and energy that you can't match. So Russ's secret to collaborating with Pablo is scheduling your meetings at the end of the day so that they can spill over. My second year of grad school, my meeting with Pablo was at 5:30 p.m. on a Thursday night. Longest meeting that semester, 3 hours, 49 minutes. One-on-one, focused attention the whole time, trying to figure out some combinatorial argument that is actually in the thesis. So thank you for that. I've been chasing night meetings with Pablo every semester since. Russ knows this because he also has an incredible appetite for persevering. The weekly meeting with Russ and Pablo is scheduled for 2 hours, and on my calendar, it is set for 3. I've been incredibly lucky to work with both of them. So the other people I really want to thank as part of this have been my committee members. So one of my former mentors at Penn told me that a great way to find advisors was to read papers and figure out which ones make you say, wow, I wish I had written this. So I tried to apply that same logic to picking my committee, and it's been a true pleasure getting to know some of the people behind some of my favorite papers during my PhD. Rob and Bart have been incredibly generous with their time in agreeing to serve on this committee and review my work, and I really appreciate the sincerity and the effort that they put into this. I also want to take some time to thank the mentors that actually got me to MIT from Penn. So my advisor, Alejandro, is actually on the call. Luis Chamon was my research mentor as an undergraduate, and Alejandro's signals and systems class is what landed me in his into research, and Luis taught me what research even was. Nikolai Matney and Manfred Morari really gave me some really great, valuable advice on picking mentors in graduate school, which is actually how I ended up with Pablo and Russ. I also want to thank my collaborators from the trenches. All of these collaborators have spent late nights iterating drafts, grinding through code bugs, refining presentations. Honkai here taught me the joys of actually writing good performant code and the impact that could have on turning a theoretical project into a practical one. Pete has pulled at least 5 all-nighters with me, trying to get things to work, several runs, coffees, just hashing out ideas and the right way to explain things. Bernard has really impacted this work at the end of the thesis. He's always generous with his times. He's got a great way of giving you completely undivided attention when you ask for help. Tobia have worked with him since my first day of grad school. He's got this meticulous attention to detail that really leaves you envying the skill with which he writes and turns his thoughts into prose. And he's just been a great person to learn how to write a paper from. And finally, Lou navigated the early years of starting the PhD during COVID with me. And her hard work at the beginning really motivated me to push through that tough time at the beginning of the PhD. I want to thank all of the lab mates that I've overlapped with over the last 6 years. It's been great learning from everyone. And it's inspiring to see the breadth of work that's happening in these labs. I don't know how Russ and Pablo keep up with everything that's happening. Finally, I'd really like to thank my family. Most importantly, my fiance, Jenna, who supported me through all the highs and lows of the PhD process. And she's been incredibly patient during every paper push, including this month-long grind through the end of the PhD. And I've been incredibly lucky to meet her during my time in Boston, and I'm looking forward to this next stage together. I'd of course like to thank my entire family, including my sister, who's actually here in person, and my brother Quentin, who's on the call. I'd particularly also like to thank my parents, who made all of this possible to begin with. Thank you for giving me incredible opportunities for education and growth, instilling me in the importance and the discipline to work hard and live up to the opportunities you sacrificed so much to give me. And finally, I'd like to thank all the friends who have really made the moments outside of the PhD really wonderful and special. Boston feels like home because of all of you. And escaping to the outdoors was always a welcome break from trying to keep up with Russ and Pablo's tireless research energy. And with that, I will take any questions. Got a mic cube.
Oh, wow. So the order of events is everybody gets to ask questions now, and then we'll have a closed session with the committee to ask questions after. So please, anything you like. There's a lot to unpack there.
In Zoom, I'm looking down because I can actually, if you turn on your camera, I'll be able to see you. I can just repeat the question.
You said a couple of times, and then you're solving your relaxation, so you don't like hear about something inaccurately.
Mhm.
Is that actually true when you're trying to certify?
So the question is it okay to solve a relaxation if you're using it for certification? No. So it depends on what you're using the relaxation for. There are 2 ways that you can think of solving the relaxation. One is I have an optimization problem and I care about the optimal value. And there the relaxation is probably more acceptable to solve it inaccurately. The other thing is I have a certification problem and I actually need to check that a polynomial is non-negative. That you probably need to solve very accurately, and the accuracy you need is a good question. So the question is, what is the critical path? The critical path is if you take the The critical path is just when you're solving this problem, you just take what is the most expensive solve at this step, and what is the most expensive stall at this step, and what's the sort of it's the serial time in the graph. And so if I had perfect parallelism, say like, there was no overhead to parallelization, what is the serial time of the actual solve? Obviously, that's an idealized time, but it's a good way of understanding, like, should you even split the maze? Probably not. You're paying too high of a cost for solving with this method. Tell me.
Do the sort of specialized computer solves like AXB or C, do those pop up elsewhere besides the Vertex program?
So the question is, does the matrix standard form show up elsewhere? And the answer is yes, it does. So the reason these show up is when you do a sums of squares relaxation, for those who are familiar with these techniques, a lot of time you end up multiplying constraints together. And that multiplication procedure is actually an outer product. And so sort of any procedure that you use in order to generate multiply constraints will generate these matrix inequalities. In fact, the Shor relaxation itself has this structure where these types of equalities show up everywhere. And this right here is a left-right multiplication. So when you have a matrix variable, if you want the vector version, you can multiply it on the right by just the all ones vector because these are homogenized, and you'd still end up with the same type of structure. If you start taking bigger products, you end up with tensor trains, which I think would actually be interesting to look at. Yep.
You did some profiling against Eager and showing that add additional constraints to make them lower. You said a bit more about the performance and this potential improvements for.
So I want to be clear, this is not an improvement on teaser. What teaser claimed and is validated is that you need to add the redundant constraints that they mention in their paper. Otherwise, the method isn't that effective. And all I'm showing is what is the effect of not doing that. And it is actually very important. So I didn't add anything new. The procedure actually recovers only the constraints that they add. And I mentioned in the thesis, we actually compute a Grosvenor basis of that, and they added everything you could. There's nothing more you could use to tighten the teaser formulation. Yep.
In C Cosmo, how much of the time are you spending looking up stuff in memory versus solving the linear system?
In C Cosmo, nothing. In Vega, 10%. Well, I mean, for the small programs, it can be like 10 to 20%. For the contact graph one, if I remember correctly, it's like 1 or 2. But the distribution of the memory is actually kind of what made writing Vega hard. Every time I thought I had found, like, I'd gotten rid of one thing, it was, oh, but you introduced another indirection, and
the linear system solve again. Is that specific to ADMM, or could you actually use that with other solvers?
So the linear system that you solve in ADMM is actually the same one is almost the same one that you solve in interior point. So all the convex optimization solvers essentially are solving some form of a quadratic program with an equality constraint at every step. That is the main computational engine behind almost all the algorithms. And so the interior point ones have the same structure.
But they're not exploiting the AXB.
No. It becomes a little bit more challenging there just because there's an extra matrix that shows up somewhere that could destroy a little bit, but it should be possible to do it. I actually write that. I actually write that one in my thesis too. What it would be for the interior point case.
when you present that kind of strength that actually have an effect on the organization, I think from like 1,000 to 3,000.
Mhm.
Is how do you reduce it?
Yeah, so the question was, how do you reduce the number of equalities that you have? So you're talking about this, like why this big gap? So what happens is that when you generate all of the valid equalities, you end up with a really, really big linear system depending on the degrees that you put on the mu i's. But there's a condition you can write down, this necessary condition that's related to degrees. That's it's related to whatever degree hat h you have. It has to be hard to prove that it's in the ideal. If it's easy to prove that it's in the ideal, it can't actually add strength because the sums of squares hierarchy will just give you that constraint for free. And so what you have to do is you actually have to add only those that could possibly help. So you can either think about forming everything and then reducing, or going from the reduced set and then trying to increment it. Since it's typically a lot smaller, the number of things that you are useful, then you typically want to do that, and that's how you get the solve times. But it boils down to a linear algebra computation. Okay. In addition to strengthening the relaxation with additional equality constraints, can we also strengthen the relaxation with additional inequality constraints? Great question, Honkai. The answer is yes. So you can add redundant inequality constraints. The reason we focus on the equality constraints is that you can search for them with linear algebra. If you want to search for new implied inequalities, you're going to need to start doing things like solving linear programs or semi-definite programs before solving your actual semi-definite program. And so finding those might be as expensive, if not more expensive, than solving the original problem. And so that's why we don't focus on that. On the other hand, the equality case, since it's like linear algebra, you can just do it ahead of time.
Okay, last question, it's great.
In data, when you split the problem,
Mhm.
data into that, do you pay a price in conversion?
Yes, and so that's actually why it's not as effective. That's why it's not as effective at the smaller scale, because you pay the price by typically requiring more iterations. So every iteration is cheaper, but every iteration is definitely cheaper. But first off, with like a lot of splitting, there's a ton of memory overhead. And so if the memory overhead is more than the cost of actually like doing the operations, then that's useless. And that's what actually happens in the maze. And then here, the graph's not big enough that you don't see enough of an advantage from the splitting to make up for the additional number of iterations you need. So that's the challenge.
All right, I propose we. We can move on to the closed session now, so, but if those of you that can stay around to celebrate with us afterwards, assuming it goes well. We'll be down at 32,380, in a little bit.
Thank you everyone online for coming. I'm going to cut the meeting now.